I know what you're talking about.
So what?
Yeah, I'll tell you.
How is that even running if it's not really on the compiler?
Yeah, so when you have a file like blah.exe, something like that,
Yeah.
when you see something like that, you recognize that as something. We would call that an executable. Why is that an executable? Why do you know that's an executable?
It's binaries.
I don't know. I think.
Here, I'm going to show you a couple other things here.
Something's gonna run if I open.
What about blah.com?
Should be executable.
Yeah.
What about blah.bat?
That is executable through the command line.
Yeah, that a bad file is gonna run a sequence of whatever we want to do. Like if you want.
So if you had an icon on your machine and you double clicked and behind it was the .exe or .com or .bat and you double clicked it, something would happen, right?
Yes.
Why?
No.
You told me you're talking about executables here, right?
Yeah.
How do you know that's an executable?
Because of the type only.
Here, we're going to do something. We're going to say blah.doc. What's that? Is that an executable?
Yes.
Is it?
Well, it.
What kind of file is that?
Document that's gonna run and.
And what? What does it open?
Oh, it's gonna open. Okay, so it's not really going to make an action. It's
What?
just gonna visualize.
Don't overthink this. What program is that going to open if I double click it?
Oh, my computer Word doc.
It'll open up Microsoft Word, right? A word processor, something that's Microsoft Word compatible. That's what that guy will open, right? All right. So here, let's. What about JPG?
Picture.
It's going to open some image thing.
Yeah.
.pdf will open your PDF reader. How do you know this guy's an executable? How do I know if I double click on it, something happens?
Do you imply that actually executable is executable by the operating system?
That's exactly what I'm implying. Okay, what's happened is this has been around for so long that we've forgotten that this kind of all started for normal people with like DOS, MS-DOS. A .exe file is only executable by the operating system
You just direct call it.
because the OS views files of type .exe, .com, .bat, I think there might be a few others, as files that should be executed.
The rest needs the program to run.
Yeah. The other ones here, the operating system views these as what are called MIME types and says, that's a .doc file. Well, I don't know how to run that directly, but I have an association in my memory that says .doc files know how to be, can be run by Microsoft Word. .jpg, the understanding of a JPG that's not written into an operating system. An operating system can look at the end of it and say, that's a JPEG. How do I know it's a JPEG? Well, I only really know that it looks like it's probably a JPEG because of the name of it. Does anything prevent you from taking a Word file, blah.doc, and renaming it blah.jpg?
No.
You can rename the file whatever you want. Your operating system is going to think it's a JPEG. And when you double click on it, it's going to try to open your image editor, your image viewer, whatever. And it's going to say, once it actually gets to the file underneath and starts looking at the code in it, it's going to say, this is something I don't know how to deal with. That is Microsoft Word document stuff. I am a JPEG editor. I don't know how to deal with that. Make sense?
Yeah, but for example, you were able to write any code in Java, but then you're going to transform that in the program that's going to be completely separated from your compiler, right? Or is it going to, right? It's not going to run with your compiler behind.
It's
How does
targeting
it-
architecture.
But how does it know? Because
How do you run the Java program?
Yeah, because
Yeah,
right
so-
now you have your compiler to understand everything.
Right. So in Eclipse, if we're using Eclipse here, we hit the little play button.
Yeah.
But under the hood, what's actually happening is it's calling the Java virtual machine. It's using a file, a program called Java.
Yeah.
All right. So the idea here is that
Okay, so
blah.doc gets opened by Microsoft Word. Blah.jpg gets opened by your image editor. Blah.class is very likely on your computer not automatically associated with the Java runtime. So if you just double click on a blah.class file, it probably would not open. So if I go in here and
Go to your bin folder.
yeah. Let me open one that actually is functional right now, because we're in the middle of working on our guy here. All right, so hello world. If I run it in here, we'll see this does work, right? All right, but I just hit the play button, it just magically works. So now I'm gonna go ahead and I'm gonna dive into my OS here. Where's my show in? Show in System Explorer. It's gonna give it to me here. I'm gonna open up my terminal. CD. All right, so now I'm out here at the command line. Here's my driver.class, this file. So if I just type in /driver.class, actually I need to do this. I need to change mod 777 driver.class. All right, so now it says I tried to run it. It tried to treat it as an executable because I seemed to try to execute this thing, and it did the best it could. It said it doesn't. This is a malformed machine code. It can't run this directly. But Java driver.class.
You should go into the folder.
Oh, am I not in the folder? I am. I'm in the folder.
Really?
But I think this is the package level thing with.
Prevention zero.
So if I here, I'll just do this real quick.
If you recompile it.
I'll just do it up here. So I'll go in here to driver. I'll say javac. I'll compile it. Driver.java. This is going to give me a local driver.class file. And now I can say Java driver. And it runs hello world. So I'm using Microsoft Word. I'm using Java to open that file. That make sense?
yeah, makes sense.
Yep. So the whole reason that this exe file automatically executes is because DOS-based operating systems or operating systems that have been, removed from DOS for a while but still have their roots in DOS view.exe files as executables. Mac does not. If I have a Macintosh file, so if I go in here and here, let's let me move driver.class to be called driver.exe. So now I have a .exe file in here, and I'll go ahead and go back into here, go into source. So here's that driver exe file.
Not recognized.
Double click on it. It's trying to open this up in Xamarin. It is allocating. It's like, okay, it's a .exe. I'm trying to figure out something to do with it. Doesn't know about it. The only way for me to open this on here would be open it with parallels. Does that make sense?
Yeah.
Yeah.
Totally.
Yeah.
No,
So
I was just wondering because I always know, okay, it's not gonna run on OS, on Apple products or Windows or Linux. It's not gonna run. It's gonna run differently. But
Yep.
I never knew why. So
Yep.
I just wanted to know why.
yeah, because it was when I compile for a Windows machine, it's compiling for that operating system as well as that architecture. And if it's for Windows, it'll be a .exe that runs.
Okay.
If it's for Mac, it actually uses a different architecture, and it does for an executable. It's actually called .app. It's sort of kind of an executable in Mac. Macs actually have packages. I don't know if you've ever kind of looked at this before, but if I go into applications here, so like we have this, like for instance, I don't know, FaceTime, or yeah, let's just go to GarageBand. If I say I right click on it, I can say show package contents. The actual executable stuff is inside here. So we look at it as you double click on this .app thing on the Mac, but that's actually kind of like a magical folder. And inside of that magical folder is all the stuff that it needs, the frameworks, all the stuff it needs to execute.
So does that has an entry in app?
Here's the Unix executable file here called GarageBand. My terminal wants access to my microphone for GarageBand, so I'll go ahead and let it have it. There we go.
Okay, it's open.
That's the actual executable.
Okay.
I don't know if I've ever had GarageBand open on this machine. I don't think I have.
That's sad.
Nah, if it's too artsy, it's not worth your time.
That's sad too.
I rarely only opened it once. My hat is my Mac.
The world takes all kinds. That's why we have all of our different talent areas. What was I doing? Oh, we're writing our
Keep programming.
our compiler. No, but these are all good questions. This is not this was not wastes of time. This is all very related to class. All right, so now getting back here. So this very first part, so an hour and a half ago, this started with her question about why am I writing this twice, right?
Yeah.
It's because we no longer have a guarantee that it's happening immediately following the previous line. So this output here will guarantee that I now have a register stored inside of destination register that has my memory address. All right. So at this point, it's when I go and write. So I have this line repeated. This line here will remain the same, nothing new here. But down here, when I do the SW, I won't do it in terms of T0. I'll do it in terms of destination register. Make sense? So here's my SW. Here's this guy. So this is where I was getting my old register name. But now what I'm going to actually put in here is destination register. I no longer need this old register name. All right, that makes sense? All right, so now at the end of this thing though, I have a temp register name and I have a destination register name. I've already written out my output.
Release.
Yep. I no longer need T1, I no longer need T0. They've done their damage for the moment. So I'll go ahead and I'll say this dot, I'm lost. What do I call it? The register collection. No, it's direct memory. This dot direct memory, right? The data memory. This dot data. See, this is what happens when we take breaks. This all has to reboot. We can just go for 4 straight hours. We're great. All right. So this dot data memory dot, and what am I doing? I am. Where's my release? Did I not write that in data memory yet? I'm not data memory. I'm registers. this dot the register collection dot release register given name. We have destination register, and then we're going to do the same thing for temp register. So I'll steal this whole line.
Yeah, we're not dealing with release memory yet.
Yeah. All right, so we're cleaning up after ourselves. All right, so in this else, first thing I'm going to do is I'm going to write that line of code a second time, guaranteed, and it's either going to be the same register as before or the correct register. Then I'll go ahead and do my output down here in terms of, I want to say here's that example. This goes back to what you asked earlier, is why are we passing it the variable name? Here's an example where we didn't want to associate it with a variable name, so we just put in just random garbage. So we kind of made that decision knowing that we were going to bump into it later on, but whatever.
I have a question back to the printing that line twice again. Because, so if we're splitting that instruction, well, I guess technically, like, the instruction doesn't have to split because
We're not splitting it. We're just allowing for them to be not next to each other.
okay. So because that like if it was where you were checking to see if it had an equal sign, then obviously that in X wouldn't be.
Yeah, well, so here's the thing. Maybe this will help. So this first line here that generates this code here,
Yeah.
the reality is that output code is relatively unimportant in our world. We definitely need that output code at least once. We actually could say, you know what? It actually isn't even a horrible thing to necessarily say that we could choose not to output anything here. Instead, what we really are trying to accomplish there is to make sure that we get a place in memory associated with that variable name.
Well, I think what's confusing me is, like, aren't we technically in a for loop going through all the instructions in our test.c file? So, like, for our if part, that's checking if it's int x, like it's saying, okay, if the first thing's int, then it's going to do that. But then for the else, like, wouldn't that get hit the second instruction, which would then be the x equals 7? So why do we have that code in our else if that technically doesn't matter at that point?
We have it in our else because we can't assign x to 7 without having the data memory that was previously established for x. And that might have been 100 lines ago. But what I'm getting at here is rather than doing it twice, so I'm actually going to go on the other extreme. What I'm saying is in this if, we could actually choose not to do anything with output. We could choose to output nothing from this if. Because the only thing we're actually wanting to accomplish in this if is getting an association between the variable name and the data memory. That's it. So we actually could say output is equal to the empty string right there. We don't need assembly output because we have only created an association with the var name and a memory address.
Couldn't you say the same thing for that code in the else though?
No, to be used later, i.e. in the else. So we're going to generate that code. All the stuff that we would have done here before, we're no longer going to do in this if, because all this if did is it reserved us a place in memory for that variable name. Now, when we actually go to utilize that place in memory inside this else, when we're giving it a value, I'm saying, hey, I want to actually put something in memory at that location. That's the point when we will need to have this code for actually establishing that connection. So when we first define a variable and we have no value that we're associating with it, all we're doing is saying, I need memory associated with that variable name. That's it. I'm not going to output any assembly because I'll tell you what, if you never do anything more than this one line, you don't need any assembly for this. You've wasted memory, but there's no assembly that says, I just want to waste memory. So we only need this output one time, and we would actually associate it with when we actually want to set a variable equal to a value.
Okay.
This line here only establishes a place in memory for holding that value.
I think in this concept, yes, when we are trying to see int I, technically we are trying to find out free memory. But actually, this memory address will be saving to a specific place in the memory for the variable, for variable tables. For just like your collection, the data memory collection. So technically, map register doing a much more things actually we see from this ADDI T0 0 than 5,000. So it has a lot of things related to.
Well, that's fine, but that still doesn't change the fact that when I initially establish a variable, I just define a variable that I don't need to output anything.
I just say that because if we are really talking about the real situation in the CPU, is not what the textbook actually introduced.
That's close enough.
Yeah.
I mean, it's not horrifically dissimilar. I mean, the textbook just tends to leave, it shows you, let's call it the two most important details, and then the 7 extraneous things that are technically important for the architecture, but not really important for the lesson, are omitted.
Yeah.
But I mean, that doesn't change anything here. We still wouldn't need to output anything from this guy.
We don't need to output that anymore.
So
then what we would do down here, just one last thing, is when I output something, I'm only going to conditionally do this. If output dot length is greater than 0. If I have something to output, then I'll output. That way we don't get just a blank line spit out. Make sense?
Yeah. So, but what if? So you're saying like obviously in the else we're assuming, or we don't really care unless it's in x and x equals 7 by each other, because otherwise, like if it just associates, that's all we really need.
Mm-hmm.
But what if? So like for instance, like it's in x, and then there's like some expression lines, and then it's like x equals 7. So it's like separated by.
Yeah, now R supports that. Because we don't actually go and get the register for it until later on. That's when we actually go and get the memory address for X.
Okay, that's right.
When we actually
So
go to
still
assign
technically-
it. Yeah, all I did up here is I reserved a nice little cozy place in memory for them.
I was thinking it had to be like right after each other, but no, that makes sense.
Yeah, but this will still work right after each other.
Well, I was thinking that was the only way it would work, but that's not. I was just overthinking it.
Mm-hmm. All right, so this guy, we'll just put a little comment here. This retrieves the Too tired to even get my joke. This retrieves the memory address of where we previously reserved this var name. That's this first part. That's what we're doing there. Okay. Then we'll go ahead and do a output plus equals \n, kick it down a line, because we're that just outputted this part, this first line here. Then we do all our old stuff that we used to do, ultimately releasing our final registers in the end. Okay. So now what I'll do is I'm going to go into Xcode here. I'm going to remove our extra line from that, and we should be able to go back and test driver here in our MIPS compiler, and there's our output that still works.
Seems like correct.
Now we can test this and see that it still works by doing this.
Copy to the.
I'm going to set I is equal to 7 later on. So now what have I done? I've created a variable I, I've created a variable j, I set j equal to something. I'm going to take the I equal to something out there. So I've done a whole bunch of stuff in the middle, right? And then I'm going to say I is equal to 7. Actually, in this case, we're going to be okay because we are still going to get the same register because we are releasing our registers.
T0.
But we'll see that we do support this in the event that we did use other registers in between. So this doesn't break our code, but it's actually not going to be overly interesting to us either. So it's still T0 where it lives.
But usually you can see 5,000 is reserved early, but used later.
Yeah. Yeah, it's true.
So memory is
Yeah.
still based on sequence.
Yeah, so you're actually seeing, it's true, you're seeing our code work. Because the first thing we see is output. If we go back to our code here, we're saying j here. This is the second variable we create. So what are we doing here? We reserve memory at 5,000. Then we reserve memory at 5,004. Then we set a value at 5,004. That's when this is actually getting pumped out. Then we reserve memory at 5,008, never use it. And then we set a value at 5,000 and at 5,000. That's this. If I then went in here and said y is equal to 2, that would have the 5,008 in the last part. There's my 5,008. So basically what we have now is a working version of last week's homework, but that's done much better, much more flexibly.
Support the thing we're going to do today.
Correct. So all this sets up for our today stuff to be relatively easy. All right, make some sense?
Can I just see the result again?
No.
Holy. Okay, I thought it was okay. Just
Yeah, so the interesting stuff here is the memory sequence because I don't actually set a value to my original variable I created until later on. This proves to us that we actually did the lookup and found what memory address that guy was associated with. This is how real, let's say, languages, compilers would work. Very similar to this. Okay. So now, let's jump ahead here and look at our expressions. So when we have a simple expression like this, where we say z is equal to x plus y, what we're going to do is we need to get the values associated with x and y. We can't just assume it's t0 and t1, right? We're going to presume we have accurate syntax. Therefore, we can go and get the memory address where, so really this line right here, this says, give me a new unused register and retrieve for me, well, before I do that, I'm going to need to get an unused register and set it equal to the address for x.
So that use add immediate.
Yep. So it's going to look like, let's identify this line first. So if I have something that looks like something equals, so we're in the x, we want to know if there's more parts. So in this else, we're going to split on the equal side, and that's going to give us 2 parts. So for expressions, we really want to find out, do we have more than just, how complex is our second part, is the punchline here.
What my solution is actually running the shunting out algorithm until there's only one feedback.
Yeah, but right now I'm trying to uniquely identify this guy from x equals 6.
Oh,
Yeah, I want to be able to say, am I looking at an expression, or am I looking at just a? Well, we don't actually have to treat them differently. That's okay. I get it. That's why you use shunting yard right off the bat, because you just said, look, here's all the values I'm going to set here. So in a situation where it's x equals 6, you're only going to have one thing in your output queue, no math to do.
If it x to y, because still will be going back to one thing, so
Yep.
it's the same.
So with that in mind, then we really can't do this part without running shunting yard first.
Yeah.
That is the good way of doing it, because what he's doing is he's effectively handling. Let me show you in notes here. Let's call this handling expressions. He's saying x is equal to 7 versus x is equal to y plus 2 versus x is equal to y plus z plus 4. These guys are all being handled the same way. We are setting a variable equal to something else, right? So that variable is going to be equal to something else, but what we're going to be doing is inside of here, we're going to have multiple sequences of things. So what shunting yard says is it deals with the right-hand side here. Notice the left-hand side is always kind of the same, right? We have a variable name followed by the assignment operator. The right-hand side, this guy, changes in complexity. So shunting yard, let's go and look at that here. So this guy deals with reverse Polish notation. So let me blow this up a little bit. All right, so it allows you to have, actually this is a good example up here because it gives you just variable names. You don't have to worry about what kinds of things they are. All right, but we have 3 different things. We have an output queue. So this is going to be our, the order in which things actually need to be processed. Okay? So our output queue up here, this is the order things are actually needing to be processed. So if I look at this A plus B times C minus D thing directly, if I look at that, I know that the correct order of operations are going to be the B times C comes first, right? Because multiplication comes before addition and subtraction. So this is just following normal math rules for order of operations. We haven't even gotten into parentheses yet. They're down below, but this handles it the same way. So effectively, if I want to do this math the correct way, I need to take order of operations into consideration. All right, so the way you process through this is you start feeding off your input. So I'm going to take the next symbol from input. This is my input queue. So you just pull things right off the front, and then you look at it and you decide, what do I do with this? So the first thing we pull off the front is an A. What do we do with an A? We just put it into our output queue. It's a symbol. It's not an operator, and it's not a parenthesis. So what do? We just put it in our output. Next thing, we pull off the plus sign. What do we do with operators? Operators we put down into our operator stack. So we push this guy onto an operator stack. Stacks are last in, first out queues. So they work differently. So I'm going to push this onto the stack. So I still have just an A in the output, and now I have the plus sign in my operator stack. Then I get my B. What do I do with B? B, I move to my output queue directly. Next thing, I have multiplication. What do I do with multiplication? Multiplication, I have to check the top of my operator stack. And I ask the question, is this guy a higher priority operator than the guy that's already in here? Which is more powerful, plus sign or multiplication? Multiplication is. So I'll go ahead and throw the multiplication on top of the plus sign, suppressing it. So now when I go to actually process this, the first math operation I'll do is multiplication. I've put it on top of the plus sign. All right, so I hit an operator here, the multiplication sign. I then looked at the top of my operator stack, And I said, multiplication is stronger than addition, so I'll go ahead and just push the multiplication on top. Then I get my C. I put the C over here in the output queue. Next, I hit the minus sign. We ask that same question again. We consult the top of our operator stack. Is subtraction more powerful than multiplication?
No.
It is not. So before I'm allowed to put subtraction on my operator stack, I have to get rid of this multiplication. So I'll pop the multiplication off my operator stack and put it into my output. So there's the multiplication. Multiplication leaves here, comes up here. So I have my multiplication there. All right. Then I ask the question, is subtraction more powerful than addition? It's the same. And when you have the same, we do it left to right. Correct? So since subtraction is not more powerful than addition, I also am going to pop the plus sign. You cannot put, the only thing you can put on top of an operator is a more powerful operator. You cannot put an equal powered operator on top of it. Okay, so only more powerful operators can go on top of an operator. Otherwise, in order to get a minus in here, I had to clear out both the multiplication and the addition. So both of those guys now are sitting in my output queue. Then I hit the D. That moves over to my output queue. Now I'm out of input stuff. So what do? I clear out my output stack. Here's my order of operation. So I process through these guys like a stack. So my math here is to take A, then B, then C. Now I hit multiplication. What am I going to do? I'm going to multiply the previous two things I hit, C times B. We look up here at the very beginning. What was the first thing we were supposed to do? C times B. All right, so I'll do the C times B, push the result back on, then I hit the plus sign. What do I now do? I add the result of the C times B and the A. Pushing the result back on. What do I do lastly? I hit the minus sign. What do I do with that? I subtract the result of my previous thing from the D. So this guy processes through an expression, giving me the correct order in which the math should be done. That make sense? Now, that's good for any kind of math. That is, order of operation is important, right? So multiplication, if we had an expression just written in our C program here, like y is equal to x plus I times j, like that. If I had no parentheses, this math should be what happens first. I should get I times j as math done first, and then add that to x. I don't want to just go left to right and say x plus I and then I times j. Multiplication happens first. So the shunting yard algorithm dictates the order in which we should cover those things. That makes some sense? All right, so next step here is we're going to go ahead and what are we doing time? 9:08. I gave you a link to, let's just write it real quick.
I think you probably can finish shunting yard in time.
Well, shunting yard's not going to take very long.
Yeah, but the whole thing probably will take longer. Because you also need a method to decode shunting yard result into the MAPC. Decode it into a set of.
You mean the breakdown thing, like what they did here.
Yeah.
So what he's talking about is this stuff here. When we go down, they talk about the more complex expressions like this. You break it down into first z is equal to whatever the first operation you're supposed to do is. Then you say Z is equal to whatever the next operation you're supposed to do is. So, I mean, this really shouldn't be that big of a deal. You're always using the left-hand side. You're just doing your expressions multiple times. You're setting them equal to the first operation. So shunting yard is going to say, here's the first math we should do. Shunting yard is going to then say, here's the second math we should do. Shunting yard is then going to say, this is the third math we should do. So on and so forth. All right. So let's write shunting yard. That'll be a fun wind down exercise. All right, so where am I at here? This is the 250 thing. I need to come down here. So what we're going to do is, instead of calling this shunting yard, I'm going to create a class called order of operation processor. Yeah, let's just call that good. And we'll put a little comment above here. This is an implementation of the shunting yard algorithm. And if we're nice to people, we can even give them a little link to this. That's the shunting yard algorithm in there. All right, so we know that we need a couple of pieces here, right? We know that we're going to need a input queue, and we know we're going to need an output queue, and we know we're going to need an operator stack. Those are the types of things that we're going to have. Things we put in our operator stack, let's just do everything with strings. That'll make our life easier with Java. So I'm going to create some private variables up here. So I'm going to create a private queue of type string called output queue. I'll create a private, this guy wants me to import java.util queue. Then I'll create a private queue of type string. We'll call this guy input queue. And then I'll create a private stack of type string, and we'll call this the op stack. And then we need to import java.util.
What's the benefit of using queue instead of linked list?
Queue has NQ and DQ. That's what the two. A queue is a simplified version of a linked list. A linked list can do all of this.
Okay.
So, I mean, the advantage is it's more accurate in terms of the tool we need. This is a queue we're feeding off of. We put these things into a line, we feed off the front of the line. That's a queue. This is the output queue. We are going to feed off the front of the line. The stack works like a stack. We push things onto it, we pop things off of it.
I apologize if this is a stupid question, but why, I mean, won't you have to convert from string back to int in order to do the operations?
We don't really
Strings?
Well, we will actually won't even have the value yet for these guys, but you're right. You're right, we will for immediate values, but in Java that's integer.parseInt.
Okay.
Yeah, so this kind of goes back to a long time ago where we just say Java is a string-based language, so all else being equal, throw it all into a string, you can pull it out easily, that type of thing. So we could be more, we could probably say the op stack actually only needs to hold chars because all of our operators are single characters, but throw it in a string, move on with life, and manipulate it. Okay, so we will, and actually, I am going to, we'll do it as a constructor. So I'll say public order of operation processor. And this guy is going to take in a string expression. And let's go ahead and give all our dudes values here. So we'll say this dot output queue is equal to a new queue of type string. This dot input queue is equal to a new queue of type string. What's it upset by? Oh, queues are not instantiable. Interesting.
And then how to declare it.
Oh, it's easy.
Q dot.
Now you probably have to write it as a linked list, but then it gives you the.
Or you can say.
Say queues are
interface.
interfaces.
So there's no benefits. of
No.
using
There is a benefit. There is a benefit. I'll show you. So we'll just remove and add. Removes from the front. Yeah, this removes from the head.
Linked list has
Yeah, but you would have to say
Link
get
list.
front and get end. So things that implement. So all known implementing classes. Linked list does implement a queue.
I just don't understand if it's a simple or why it's okay. Anyway, it's fine.
Well, what they did is they said that this guy is a queue is one of the many things that linked lists adhere to.
I see.
Okay, but by me treating them as queues here, I'll only get access to the couple of things that I want. I'll show you what I mean here in a second. So I'll import java.util linked list. So I'm going to create in this variable that's capable of holding a queue. Now, this guy is something that, when I say holding a queue, this guy is something that adheres to the queue interface, is what that's saying. That means he has the add and the remove function.
Yeah.
Very simplified. I'm going to go ahead and fill it up with a linked list, because a linked list, as the documentation tells us, is one of the things that implements the queue interface. So I'll do the same thing down here.
Linked list has all the potentials of queue,
Yeah.
but because you
Linked list implements several interfaces. So if I show you here, if I click on linked list, here's all implemented interfaces. A linked list implements serializable, clonable, iterable, collection, DQ, list, and queue.
But the
It
queue,
fills the role of
Yeah.
all of those things.
but the queue only have its own.
Queue only does two things. That's all we needed to do. And it makes more sense for us to say, if I need a queue, I will create a queue, because this guy, let me just show you here. So I'll say this dot output queue dot. Notice this guy has an add, which adds to the front, and he has a remove, which removes from the queue. It doesn't have all the other little things that you can do with a linked list, like add end, things like that. Remove some of those things, even though there's still quite a few things in there. All right, so similarly, we'll go ahead and say this dot op stack is equal to a new stack. Is stack a thing?
Yeah, stack is.
Stack's a thing. Okay, there we go.
But queue.
And then we'll say this dot op stack should have a push pop. There's a push, there's a pop, there's a peak.
Yeah.
So our three stack things. Okay, so we need these three buckets represented for shunting yard. Now I need to go ahead and process through this expression.
Yeah.
Now, our expressions are going to look like, could be something like this. That's what our expressions are going to look like, right? So I need to split this guy up. So now we could pass it. I'm probably actually going to just pass it this part.
I only pass the right part.
Yeah, so our expressions that are coming in will actually look like that. That's the math we need to do, and we want to get the correct order of operations out of that guy. All right, so what I need to do is we may or may not have spaces in there. So I'm going to go ahead and I'm going to quickly remove all the spaces. So I have just a string with no spaces. All right, that way I only have variable names and literals and operators. Make sense? So I'm going to just write a quick little, well, do I even need a function for it? I'll just write it in here real quick. All right, so I'll say string answer is equal to, you know what, I think we have,
String space.
I want to say string buffer exists and it already has a,
Type.
to remove spaces. Or remove, you know, elements of a certain type.
Oh, I don't know. There's this class called string buffer.
It's called like remove something.
String buffer.
Didn't find it immediately, so we'll just write it. I'm going to say string answer is equal to the empty string, and we're going to go ahead and spin through every element of expression that is not a space, and keep everything that's not a space. So I'll say for char C in expression,
You count. What?
and I'll say,
You count.
oh, it's not iterable.
Yeah, you have to using for I side.
For I is equal to 0, I is less than expression dot length, I plus plus if.
But why not using a replace all? String dot replace all. Then.
Could I replace it with nothingness?
Yeah, we can replace the space with empty string.
Oh, because it does a replacement for string.
Mm.
Yeah, we could do a replace all. But I'm far enough down the line, I'm just going to finish writing it. So dot char at I, if this guy is equal to a space, well, I actually want to say if he's not equal to a space, I want to keep him. So I'll say answer plus equals expression dot char at I. And then we'll go ahead and say expression is equal to answer. So that will remove spaces from expression. That's what that code does. So afterwards, expression is now equal to the spaceless version of expression. All right, so now I want to go ahead and split this guy on his operators. Now, we have a cool tool already built into Java for doing this called the string tokenizer. So I'm going to say I want a string tokenizer. ST is equal to a new string tokenizer. And I'm going to pass it, and this guy's in java.util, I think. And I'm going to pass it my thing I want to tokenize, expression. I'm going to pass it a string containing the various tokens. For right now, I want to tokenize based on plus, minus, times. I'll put divide in there even though we don't support divide. And then opening and closing parentheses. Those are the various things that I might find that are not variable names in my expressions. And then I'm going to give it this last parameter that says true. That last parameter says, do you want to keep tokens?
Yeah.
So this says, because if I were just to give a string tokenizer on my expression and my expression looked like y is equal to x plus w plus 2, let's see, times 2, let's say, like that. And I were to say I want to tokenize this guy on all this stuff, I would only end up with 3 tokens. I would end up with an x, a w, and a 2. I actually do care about my operators. I just want them to be separated. So by saying true, I'm saying I also want you to give me the operators. So by doing that, it's going to give me an x, a plus, a w, an x, a plus, a w, a times, and a 2. That's what the tokenizer will have in it. Those things. And now I can process through those things and put them into the right place. Now I care whether or not they are an operator, right? I care whether they are either a plus, a minus, a times, whatever. So I'm going to go ahead and I'm just going to write a little private function here, Boolean, called isOp. And this guy will take in a, we'll have it take in a string as a parameter. And this guy's going to return true if that string is either a plus, a minus, a times, a divide, or a opening and closing parenthesis. It's one of those guys. Okay? So we know it'll only be a single character. So I'll go ahead and say char c is equal to s.trim.char at 0. So if in case there's any spaces, there wouldn't be because I removed spaces. But I can trim it again. You know, you never get too close of a shave, I suppose. All right, so now I have my operator in C. So I'm going to ask the question. Well, I'm going to say return C is equal to plus or, I'll do it all in one line. C is equal to minus or times or divide or open parenthesis.
Why not using your famous index of equals to larger than minus 1?
Oh yeah, I do like that one. That is better.
I thought that is your favorite.
It is one of my favorites. We're going to stick with this. Too far down the line. All right, so we're going to write an or saying if it's equal to a plus or it's equal to a minus or it's equal to a times or it's equal to a divide or it's equal to an open parenthesis or it's equal to a closing parenthesis. If it's equal to any of those guys, it'll return true. Else, it'll return false. Okay? What he's saying is I could have just said return.
You can copy that.
Yeah, I could take this string here and say return that dot index of C.
Greater than minus.
Yeah, not equal to -1.
Mm-hmm.
So that does the same thing. Index of gives you the first index, the first position in a string where something occurs, or -1 if it doesn't. So if this guy is something other than -1, that means we found it in this string. All right, so that's our isOp. All this guy will do is he'll return true if it's one of my operators, false otherwise. That's what he does. Okay, so now I'm going to process through my tokenizer. So I'm going to say while st dot has more, well, it has more elements, has more tokens. I think they both do the same thing. Has more tokens. So as long as I have something that's still in the tokenizer to deal with, I want to grab the next token. So let's create a little variable here called curToken. And we're going to say curToken is equal to st.next token. So I've taken the token. Now, one thing with a string tokenizer, though, is when I remove a token, it's actually removed from the tokenizer. So when I just said st.next token, the token I grabbed is no longer on that tokenizer. The tokenizer is one smaller than it used to be. That's why I preserved it inside this variable. All right. So now I want to ask some questions. If this token is not an operator, what do I do with it? I just put it on my output queue. Right? So if not this dot is op curToken. If the thing I'm looking at is not an operator, what do I do with that automatically? I say this dot output dot add curToken. If he's not an operator, my only option is to put him on the output queue. That's this move right here. I'm looking at something that's not an operator, this A. What do? I put him onto my output queue. Okay? Else. If I'm in here, must be an op. So now I have my rule. Only more powerful ops can go on top of an op. Something like that in the stack. All right, so what I need to do is I need to make sure that the whatever's currently at the top of my stack is not more powerful. Well, I need to make sure it's not less powerful than the guy I'm trying to do something with, right? So if he's weaker, I need to start clearing my stack. Mm-hmm. All right.
No weaker, right?
So I need to now have a function that says, so maybe we call private, let's call this guy can push. And this will take in a string op1 and a string op2. And he's going to return, so it says this guy returns true if op1 can be pushed onto op2. That's when it returns true. So now we need to talk about the order of operations. All right, so we're going to say op2, we're going to give these guys some values. And we can do let's see, plus, minus, times. It's not going to work for. I was going to do something fancy there, but it's not going to be as clean as I want it to be. So what I'm going to do is plus minus times divide, something like that. And we'll go ahead and put our opening and closing parentheses there. Closing we actually treat differently, but you know, we'll just leave it for now. And then I'm going to have string powers is equal to 0, 0, 1, 1, 2, 2. So a 1 is stronger than a 0, a 2 is stronger than a 1 for order of operations. So now what I'll do is I will say int op1 pow is equal to powers dot charat map dot index of op1, and that's going to give me a character. I'm going to say integer dot parseInt of the empty string concatenated with that character. So this guy will give me the position of op1 inside of map. So 0, 1, 2, 3, 4, 5. Powers.charat at that position. So if I gave it a minus, my position was 1. Powers at bucket 1 is a string 0. Well, it's a char 0, which I'm then turning into a string, which I'm then getting the integer version of it. So op1 pow would then be equal to the number 0. Similarly, op2 pow. I'm looking up op2. All right, and I want to return true if op1 can be pushed onto op2. So that means that op1 pow is greater than op2 pow. Return op1 pow greater than op2 pow. That makes sense? So get the powers of my two operators and then return true if this one is stronger than this one. And I'm allowed to push it onto my op stack. We can even say can push onto op stack. We want to be real explicit here. All right, that's what this guy does. So as long as we can't do that, I need to pop things off my op stack until I can do that. So while op stack, what was it? This dot op stack dot was it size? Dot size is greater than 0. So as long as I have something on my op stack and not this dot can push onto op stack, what? My cur token, it's taking it as a string, right? And the current top of my op stack, this dot op stack dot peak. I'll kick that down the line there. So while I have something on my stack and I can't push the current token on top of the stack, what do? I add to my output, this dot output q dot add this dot op stack dot pop. And then I'll try again. So as long as I still have things on my stack and whatever's at the top of the stack is not something I can push on top of, what do? I add to my output queue the top of my stack, and pop removes it from the top of the stack. As soon as I get here, I am now free to push onto the op stack for one of two reasons. I've either popped it enough times to now give me a clear landing, or it's now empty and there's no reason why I can't put a new thing on there. One of those two things. So I can say this dot op stack dot push cur token. Like that. That makes sense? All right, now we do have one special thing here that we haven't accounted for, though. The parentheses, yeah. So just for the moment, especially since for time, well, actually, it wouldn't be a big deal to just handle it. If we're looking at a closing parenthesis, so the idea is when I hit an opening parenthesis, that's definitely super powerful. So I could push an opening parenthesis onto the op stack. Always in my world right now, right? But when I hit a closing parenthesis, I need to do something special. A closing parenthesis says, I'm not pushing anything onto the op stack, but I need to pop off my op stack until I hit my opening parenthesis. So if I'm in here, I really want to have a special case. I want to say if cur token dot equals the closing parenthesis, I need to pop until we find the opening parenthesis. All right. So if I'm looking at a closing parenthesis and we assume that the expression was accurately written, I'm going to say while this dot opstack dot peak dot equals so while it's not equal to the opening parenthesis, I'm going to say this dot output queue dot add this dot opstack dot pop.
Then pop.
As soon as I get here, that means the top of the stack is the opening parenthesis, which does not make its way onto my output queue. So I just say this dot output queue dot pop. Just burn it. I'm not putting it anywhere, just pop it off the stack. Make sense? That's what I do. If I run into a closing parenthesis, that means I just hit the end of the stuff that's very important. So I'm going to start grabbing all the operators that I've run into since the previous closing, since the opening parenthesis, and get them onto the stack.
So that's gonna treat has like more than one parenthesis?
Yeah, this will work for any number of parentheses, yeah. Else, I'm going to do all this stuff. I must not be looking at an closing parenthesis. I must be looking at something else. So that if we want to not be deceptive, what we would probably do is down here on the can push onto the op stack, we'd probably get rid of that closing parenthesis and that last two. Because I would never actually ever ask a question about closing parentheses here. Closing parentheses trigger me to clear my op stack until I hit the opening parenthesis. Okay. And this is not the output queue. This is the op stack. All right. So if I hit the opening closing parenthesis, I get all my operators in between onto my output queue. Else, I figure out whether this is something I can deal with or not. All right.
End of the loop.
Yep. So this is what I do for all of my tokens. So when I finally exit out of here,
Next.
Yep.
Closing bracket.
my output queue is now in order of operations, something like that. And then what I can do here is I can maybe, well, let's just display it. So we're going to say for string s in this dot output queue, we'll go ahead and say system dot out dot println s, just kick it down, and that'll be the order of our things. And now we'll go and test this.
You have to put the operate stack empty. You have to pop.
Oh, yeah. So output queue is not quite in order. So when we get to the end of our input queue, we might still have a couple of things stuck in our op stack. So I just need to do clear op stack. So while op stack dot size is greater than 0, I'll say this dot output queue op stack pop. Because I'm done with input stuff. Now I just need to clear out the rest of my op stack. So now everything that I was processing is now sitting on my output queue. Then I'll go ahead and print out my output queue just for testing purposes. Okay, and this is an order of operations processor. So I'll copy this guy. we'll go into our driver here, and I'll comment this out rather than dealing with source code for a second. I'll say this guy, ops is equal to new this guy, and then I need to pass him a string, and I'll give him a string sample from this. So this is A plus B times C minus D. A plus B times C minus D. And I can put spaces and stuff in there. And
More real testing.
yeah.
And you can add.
So here's my ABC times plus D minus. ABC times plus D minus.
Awesome.
Give me my right output. And I can, throw all sorts of crazy spaces and things like that. And if I want to, for some reason, do the minus first. Row, empty stack exception. What'd you do?
Break.
I got an empty stack exception with this. C minus. So it was just when I put the parentheses in there, right? Yep.
Yeah.
All right. Well, that should be easy enough to find. So we have in our code for dealing with parentheses, I'm looking at a closing parenthesis, pop until we find the, okay, so that means that I'm running into the empty stack. I'm trying to pop from the empty stack when I'm looking at the top of the stack. So while the top of the stack is not the opening parenthesis,
So
pop. So that means I'm never actually getting an opening parenthesis onto the stack. This guy here, I would hit the opening parenthesis. We would ask, can that go on top of a multiplication? Should be able to. So let's go to our.
How about you try to delete the closing parenthesis?
Well, the closing parenthesis should be there. Can push on top of stack. I'll just turn a breakpoint on right there, and I'll run my debugger real quick. Oh, that's a very weird.
I hate the debugger in Eclipse.
That's what I was just thinking. Yeah, we're not going to do that. Okay, so we'll just do this the old-fashioned way. All right, so I have 0, 0, 1, 1, then 2. So I would be passing in, I just want to make sure my orders are here. So op1 and op2 return true if op1 can be pushed on top of op2. So op2 would be the top of the stack. Op1 is my current value. Is that the way I'm passing it?
Why not just print the op stack?
Well, let's just test my logic, my obvious logic real quick. So when I call that guy, where's my, if it's an op, well, if it's not an op, do this. Oh, hold on. How do I test for ops? Okay, well that should flag correctly. So if the current thing I'm looking at is not an op, then do this stuff. If I'm looking at a closing parenthesis, do some other stuff. Else, as long as the op stack, all right, let's make sure these are in the right order. So I'm saying this is the thing that I want to push on top of the stack.
But if it is wrong, the output should be wrong. So I don't think that is the problem.
So op1, true if op1 can be pushed onto op2. So op2 is my peak, and this is the thing I'm trying to push on there. Op1 pow, powers chart map index of op1, 2 pow. So I am allowed to push it onto the stack if the power of this operator is larger than the power of the top of the stack. I can always push a more powerful value on top of an element of the stack. So this code looks correct to me. So with that in mind, what we'll go ahead and do is, when I see this closing parenthesis, because this is where we're dying, let's just quickly spit out our, I wonder, can we directly print a stack? So we'll say this dot op stack.
Yeah.
So right before it dies, it should give me an output. So that's my op stack. My op stack just has a minus sign in it. It does not have an opening parenthesis.
Why is the reaching except? Oh.
Yeah, it's dying on the very next line.
Yeah.
But that's the last thing that happened. So that's kind of like having a breakpoint.
Let's go back.
Let me see what my guy looks like. It's this.
Minus.
Okay, so I'm getting. So the top of it right now has this guy in it.
It's not like wrong. It should be.
Let's print it multiple times.
It should be. Everything should be on top. Oh, minus clear up the parentheses. Because
oh, we cleared it out. Yeah. Where this thing, when we go and find out whether something is more powerful, can go on top, we couldn't put the minus on top of the parenthesis. So really, it's our logic right here. Where's my...
Parentheses can put on everything, but everything can also put on parentheses.
Oh. So that means we just do this.
But that means parentheses cannot do anything.
Oh, we need to treat it as a special case.
I don't think it's.
Yeah, so then what we'll do is this. We'll just have our numbers like that.
Yeah.
And then we'll treat parentheses as a special case. So if the current token is equal to that, do that. Else if current token is equal to the opening parenthesis, then we'll just say this dot op stack dot push cur token. No questions asked. Just put it on top of the op stack.
Yep. Wait a second. Are you still going to compare anything with the? I think it's still about to compare. You still need to add that can push. Wait a second. How do you correct it?
Well, you could always put an opening parenthesis on top of anything.
Everything, but everything can also be put on the opening.
Oh, right. So then the fix is what I said before. We're comparing. So if I say I'll make this 1, I'll make this 0, 1, 1, 2, 2.
Yeah.
And we'll have an opening parenthesis right here. That makes the opening parenthesis weak to anything that would go on top of it, but we're handling putting opening parentheses
in a different logic.
Yeah. So there's our output for that. And now we find it. All right, so this guy has our stuff now in the correct order. Let me take that print statement out of there. Okay, so now that I have that guy set up in the correct order, the homework is actually easy.
What?
Because now I have my expressions, because now we're right back to what we basically did last class. Last class, we did a series, so if we just look at the simple model here, we did a series of, if something looked like this, what did we have to do? We went ahead and we got our, here's the output for a simple instruction like this. So if I say z is equal to x plus y, this guy assumes that x and y are in T0 and T1. We have code already now to look up, what those memory addresses are and load them in there from memory. All right, so we'll go ahead and load into some register the value. Now, then we have our add. So depending on what this operator is, we're going to add, but we're going to be determining this stuff by walking through our output queue here. So as I walk through this, I'm going to grab the A, then I'll grab the B, then I'll grab the C, then I'll grab the D. Then I get the minus. Minus says do some math. So the very first thing I'll do is I'll set, what's my operator here, Z in our example. So was that what I had in here for my... Oh, I'm only testing it on the second part. But let's say this was a Z equals this. What we would do is we would treat this as Z is equal to each one of these things in order. So when I run this, the first thing I would do is I would output the assembly code for Z is equal to C minus D. That's the first math that we do. Then I would do Z is equal to Z times B. Then I would do Z is equal to Z plus A. So I'd have the simple output for those things. Okay, so I mean, legitimately, after all that work, this is probably 10 minutes from being complete. Is the punchline, because we just need to process this queue. Now, does that kind of make sense? So all the things that we did today were in preparation for processing the output queue of the shunting yard algorithm. And I'll point out that I think in the assignment I gave you an implementation of shunting yard, right?
I didn't see.
Yeah, but I did give it to you. Or did I put it on Slack? Did I put it on Slack?
I only see the wiki. I didn't really pay attention to it.
Yeah, all I saw was that one link that you just scrolled over that one.
Are you lying?
Yep. No, I'm not lying. I'll say that's it.
I don't know.
It's a little late. I'm sorry.
I don't even try to look it up, because I believe it's not universal.
Well, I thought I gave you a Java implementation of it.
Oh, I didn't look there.
Give me the code from class.
Not at 10 o'clock, no.
No, that's good. So it might be good when it's 9 p.m.
Mm-hmm.
I really remember giving that to you.
It's fine. We accept it.
Oh, it is not fine. You better find that.
Well, no, you should have been able to write this. This wasn't that bad, but I did intend to give it to you.
That's the answer. I expect you to write.
Well, so what's concerning is that several times didn't I say in here I gave you the code for it, and nobody said no, you didn't?
But we thought it was the link that we were reading.
Yeah.
On Wikipedia.
We thought you were just talking about that.
I didn't even try to see if there's an implementation.
GitHub.
You
Because
had high expectations of us, so that's why we thought it was just assumed. Yeah.
I just create on my own. I don't
Shunting.
know what to find.
Try.
I mean,
Yeah.
Maggie sent our group your shunting yard one, but she sent that today.
she is.
Yeah, maybe that's it. I think that's it. Because, right. I did send a message the other day saying that people haven't asked questions about the homework yet because otherwise people would be questioning about shunting yard. And then I guess it must have been Maddie who asked me, about shunting yard, and I gave her a link here to this repository that has shunting yard in it. I have a couple different implementations of
So
it.
you only sent it to one.
I asked it for the student who asked.
I mean, I didn't ask.
Start your homework earlier and ask.
I saw the wiki, so I don't know why.
Yeah, well, I mean, and the thing is, this is definitely writable. There's nothing crazy about this algorithm. So if a grad student in computer science should be able to write this algorithm. This isn't anything crazy. So it's, I don't know, it's not a strong argument. Most of the hard stuff that we had to do was modify the old code to make it give us the ability to release and grab direct memory. The shunting yard thing wasn't that big of a deal. At the very least, if you completely ignored shunting yard, you could have had this work for left to right assumption. Everything is operating left to right. Order of operations just out the window. Should have at least worked for that. So I guess when I grade it, I'll look at that and I'll say if you have it working, but it doesn't take order of operation into consideration, I'll give you credit. But you should have been able to write shunting yard yourself. And there should have been more than one question about shunting yard if you were concerned about writing it yourself. Okay, so I'll give you this as a starting point. So what is the next thing after?
I would say chapter 6 was really, really difficult.
Well, with memory?
Like, it was even more difficult than chapter 5. And we spent almost 4 hours discussing chapter 5 in class.
Wasn't chapter 6 just DRAM and SRAM?
I thought it was really confusing.
When it gets to memory cache, it gets really weird.
Well, all cache is SRAM. Just talks about, most of the chapter was what yields for, it kind of talks about the industry of architecture. That SRAM is way more expensive than DRAM, and cache, the closer to the processor, is typically done with SRAM because it needs to be super, super, super fast, but it also makes it more expensive.
Yes, but those were like only 3 chapters of the chapter, whatever.
So what was the difficult, what was confusing?
Like cache, part 1, part 2, and had that self-associative cache that wasn't pretty.
Oh, so the cache thing, the way that you had to access how it's almost like a hash table for accessing cache stores, because cache works on this hit system where it says the idea is cache is supposed to make things fast if it's there. So you have to have this really quick way of just checking. Do you have the value for me? If not, I'll go someplace else and waste my time. But I want to check really, really quick if you have the value. So that's why they use this hash algorithm with like a couple of bits, so you can just see, is the value available to me. I could see how that might be a little bit.
I wish that we would have spent like a good hour and a half talking about this chapter.
About chapter 6, really?
Yeah. And we didn't even finish discussing chapter 5 last week.
Yeah, we are on 5.7.
Yep. That's as far as we got.
But the rest.
But this stuff was not.
Yeah,
after talking about all this stuff, I thought that's how we left it last week. Is after
Still,
talking about all of this stuff, we would.
it was still difficult after 5.7.
Because when 5.7, that's when you start actually design the full map of the processors and how all the things actually happens.
That's why I asked a question. Do we really need to understand everything, how actually every component works? Do we need to remember when if it's add, which one need to turn this to 1, which one turn it to 0? That's a little hard to remember.
All right, let me look at this. That's the simulator, right? All right, so then for next week, read all of chapter 7. I realize that you say you struggle with 6 and we need to cover the rest of 5. So read all of chapter 7. I'll give you a homework assignment that doesn't involve either of those and takes less time. Or I might even see if there's something I can find that will give you more practice with the stuff from 5 and 6. And then we'll spend time next class finishing up 5 and talking about 6. And presumably talking about 7.
Yeah.
Because it sounds like, I mean, if I'm just kind of doing the math here, it sounds like anything dealing with software, we're getting a grasp on. Anything dealing with hardware, we're lost.
Yeah.
Is that fair?
Yeah.
It is true.
Okay. So we'll spend time on the second half of 5, 6, and presumably 7 next class, and then we'll talk about the midterm.
Cool.
Okay.
Sound
Thank you
sound
so
good?
much.
Sounds good.
Are we
Thank
gonna
you.
finish
That's awesome.
doing the rest of the whole, like you said, there was only 10 minutes left of what we needed to do.
Yeah, we can do that. I'll finish writing that solution at the in class next time. Maybe we'll talk about this hardware stuff first, and then do that, or maybe I'll even just write it and put it out there and explain what we were doing. But it probably is valuable to see the end of the shunting yard algorithm by talking about it in class. So maybe what we'll do is we'll start off next time and just finish that real quick and just call that good for the compiler based on time. And then we'll spend the rest of the time next time talking about 5, 6, and 7 and the midterm.
Yeah, but if you find something that like for like a homework thing just for us to do, like dealing with 5 and 6. I
Yeah,
think
that's what I'm going to look into. So give me until maybe noon tomorrow for put your homework assignment up, and I'll find something beneficial.
Thank you.